Good morning, welcome back. Happy Monday. Today we cover a brand new topic called Power Series. Today, quiz number 5 is due, so make sure the quizzes are in the folders right now. They're due right now, don't turn them in late, turn them in now. Project number 8 is officially assigned. It's going to be due, it looks like, when? 1 week from today, I think that's right. Monday coming up is project number 8 due date. There is one more project after this one, but project number 9 is a reflect on the semester and what you've learned. It's going to be writing and talking about the course. It's not a math project per se. So this is the last hardcore math project of the semester. Any questions on the calendar? We got one more quiz very near the end of the semester. Other questions? Okay, so here we are, top of page 41. We're actually going to skip around a little bit here, but we'll start with our daily summary. In this class, we extend our work on the series of numbers, that's what we've been talking about for the last several classes, to series involving a variable. So instead of just having summations of fractions with only numbers floating around, we're going to talk about summations of things with x's in them. These are called power series. So here's the definition. We're just going to skip right to something concrete down here in number 3. It says consider the power series in this guy right here. 1 plus x over 5 plus x squared over 25 plus x cubed over 125, etc. going forever. So we can think of this guy as a polynomial, except how many terms does it have? Infinitely many. So it's not technically a polynomial which has finitely many terms, but there's a polynomial kind of with infinitely many terms. Now, if you plug in x equals 17 and you just do this summation forever, what do you get? Infinity, right? And if you plug x equals 17, it's going to blow up and go to infinity. If you plug in x equals maybe 0.1, perhaps it won't be infinity. And so what we're going to talk about is what kinds of values can we plug in for x, which gives us something finite, and what values is it infinity. So we've got a few specific values down here, but let's first get some practice writing this guy in what we call closed form. This is number 3, meaning with sigma notation. So here we go, summation. So the basic idea here is to pick apart that pattern. What is the pattern here? I see a fraction, so I'll put a fraction line. All right, so I hear 1 vote for x over 5. This? What do you think? Does that capture the pattern? Power on the x. Yeah, and then we'll just have to pick the right starting value here. So the way that we've got it set up right now, where does it start? N equals 0 will give us the first term, which is 1, going up to infinity. There we go. So that's what we call closed form for that power series. Okay, let's come down here and we'll just do one of these numbers. Let's just do part A. If we plug x equals -3 into that guy, I'm just going to write it as -3 over 5 to the n. What kind of a series is that? It is geometric, right? What's the ratio? Magic multiplier is -3/5. That's what the -3/5 to the n is doing, is saying just keep multiplying the previous thing by -3/5. And what was the interval for convergence of a geometric? 1 and 1, yeah, between -1 and 1, right? And so -3/5, does it live in our convergence interval? It does. So that series is a convergent geometric series. With x equal to -3/5. We knew lots of stuff about geometric series before we talked about alternating series. So you could find the actual sum. We've got our formula, the a over 1 minus x. You'll just get some number. You get what you get. The important question is, does it converge or diverge? And it converges at x equals -3. We're not going to write it out, but if you put a 6 right up there, what kind of a series is that? It is still geometric. And the magic multiplier here is 6/5. Converge or diverge diverges. And so we can analyze this thing with the x in it and discover that there are some values of x for which the series converges and some values of x for which it diverges. So in some sense, we're doing like an infinite number of geometric series questions embedded inside of this one problem. So let's come down here and talk about number 5. It says, for what values of x will the series converge? So let's write it out here. What we need is for our magic multiplier to be trapped between -1 and 1. Yeah, in the general power series, what was the magic multiplier? It has x in it. So you're giving me the final answer, which we will get. But what we need is for x over 5, which was the magic multiplier, right? That's what you multiply every term by to get the next, to be between -1 and 1. That's what we know about geometric series. So we multiply everything here. We're just trying to solve for x. And so to get rid of this divide by 5, we multiply everything by 5. And so if we multiply everything by 5, we get -5 is less than x is less than 5. Everybody see how we did that? You guys have a lot of practice with inequalities where there are just two sides and one inequality symbol in between. Well, here are 3, I don't know if sides is the right word, but it's the same rules of algebra that you can do on the ones you're familiar with that still apply to these ones here. So we multiply all 3 pieces by 5, inequalities stay the same. Okay, number 6, your answer to the previous question is the domain of the power series, and it's called the interval of convergence, which we will abbreviate IOC. If you pick any number for x between -5 and 5, what can you say about that series? It converges. If you pick any number outside of that interval, the series diverges, including the endpoints, right? X equals 5, x equals -5. Okay, interval of convergence, IOC. Number 7. Here's another power series. So this one is more complicated. So first of all, there's x minus 2's floating around every place. That's a little bit different. Also, is this a geometric series? It's not. You're not going to be able to multiply by something to get this 1/4 and then again the 1/9 and then again the 16th, right? That is not a geometric series. So this question right here is very similar in nature to the questions on the project that I just handed out today. Again, make sure you grab one. So the process that we're going to follow here is what you're going to do 4 times on the project. So here we go. First thing we need to do is write the series in closed form. So we'll get lots of practice writing things in sigma notation. So we're going to capture the pattern. We got 2 basic patterns to, well, 3 kind of patterns to worry about. First of all, I see fractions, so I'm going to write a fraction line. Anybody know the fancy word for fraction line? We're gonna write it up here. Fancy, fancy, fancy. It's called the vinculum. Yeah. You'd be surprised how often that comes up in conversation once you know the word. Okay, so I see x minus 2's to a bunch of powers. So x minus 2 to the n, sure, why not? And then on the bottom, what kind of special numbers do you find? These are perfect squares, right? So let's call it n squared. Not sure, it might be n plus 1 squared, it might be n minus squared, but it's something like that. And just a key here, you're not looking to say, oh, all right, I increased by 5 here and I increased by 7 here, and it's true, there's a pattern there, but you aren't going to be able to write that pattern in closed form. You're not looking from one term to the next to see how do I transform one term into the next. You need a formula that will directly zip you to the 17th term in the series, like n squared. Okay, and then the other piece of the pattern is this alternating business, and we've seen that before. So the way that we get the alternating pattern is to put a -1 to a power. My default is to just put an n and then check, and if I need to amend it, then I will. But it's just a good starting place. Okay, so let's try this guy. if we pick, for example, n equals 3, then upstairs we get x minus 2 to the third. So apparently we're talking about this term right here. Downstairs, what do we get? 9. So that worked out just fine. And then if we plug n equals 3 in for this guy, what do we get? Negative. And is that what we wanted? No. So then we'll just tweak it and make it an n plus 1, or n minus 1 would be fine too. So plus 1. That's first reading. Yeah, and then last thing is to find the bounds on the summation. So Yanni says n equals 1 is the start. Is that right? Yeah, because 1 is that power up there going to infinity. Okay, closed form. All right, now we don't have a simple geometric series thing where it's just like, oh, as long as the magic multiplier is between -1 and 1, then the series converges. What we're going to do is use the ratio test, which is really common for power series. Ratio test, ratio test, ratio test. Let's give it a shot. So remember, the ratio test says we're going to do a big old limit. I'll call it L. As n goes to infinity of, the ratio test doesn't involve bringing any other series into the question. We're not comparing to anything. So ratio is a fraction. Which one goes on top, the current term or the next term? Next term. So all of these n's become n plus 1s. So we got -1 to the, it actually becomes n plus 2, right? If you change the n into an n plus 1, then it reads n plus 1 plus 1. Maybe we'll just write that, n plus 1 plus 1. Next one, x minus 2, that n becomes n plus 1. Downstairs, that n becomes n plus 1. So it's that. Avoid the common mistake of putting the n squared down in the bottom and then saying, okay, we do plus 1. That's not it. Right? And this is a very common mistake, is to say, oh, okay, it's n squared, and then I'm just adding 1 everywhere. It's not this. It's replacing the n with n plus 1. Okay, there's that guy. And then we divide it by the current term, but let's just go ahead and save some writing and immediately flip it over with a multiplication. So flipping this guy, let's see, n squared on top, x minus 2 to the n on the bottom. I'll put the -1 to the n plus 1 down here, but it doesn't much matter where that guy is. So it turns out it's really important for us to put absolute value when we do the ratio test on power series. That hopefully will become clear in just a couple of minutes, but we'll include it every time. Okay, and now we got some algebra to do because we need to clean this limit up. First of all, what about the negatives here? They're inside of an absolute value, so they don't contribute anything, right? We're just going to ignore them. I'm not going to cross them off. I'm just not going to write them again. So next thing to do is look at these x's. So I got x minus 2 to the n plus 1, x minus 2 to the n. What's left over when we cancel? X minus 2 where? On the top. So in absolute value, upstairs, I've got an x minus 2. And then also upstairs, I've still got an n squared, and downstairs, I've got an n plus 1 squared. Okay, I'm going to do something kind of strange here. I'm going to write x minus 2 in the front of the limit. I'm going to put parentheses here. Don't copy that because we're going to have to tweak that in a second. But that's a really strange thing to do because when you have limits, you're not supposed to, what are the things you're allowed to take outside of limits? Constant, like a constant multiplier you could take outside, right? But x minus 2 has x in it. And you're not allowed to just pull variables willy-nilly out of the limit. But yeah, what's the variable with respect to that limit? Is n, and x is a constant. right? And so it looks strange in the beginning. And if this variable down here if it had been x going to infinity, then there's no chance I could do what I just did. But x is a constant. No, because the n, yeah, in that case, yes, you could take the n's out. All right. But when I take the x minus 2 outside, I put these green parentheses here. That's not quite right. X minus 2 was inside of what? Absolute value. It's still in absolute value. All he did is pull it out of the limit. So what we need to do is put absolute value just like that. Okay, so let's look at what's left in this limit. First of all, the absolute value makes no difference anymore because n's are all positive. X could be a negative number. I don't know anything about x, but n's are certainly positive. So I can ignore the absolute value here. And what is that limit? 1, because the bottom power is n squared plus stuff I don't care about. And the top is n squared. And the n squareds are exactly the same as each other. And so this whole limit goes to 1. So that means that my final answer for the limit here is the absolute value of x minus 2 times a 1 there. Question so far? So the limit piece went to 1. Yeah. Yeah. Okay, so let's come back to basics. The ratio test has a conclusion. It says if your limit satisfies some condition, then the series converges. What is that condition? Less than 1. That's what the ratio test wants. If the limit is less than 1, then the series converges. So out of the blue, we'll say, okay, I really want the series to converge. We're going to force this thing to be less than 1. Make the limit less than 1. And if absolute value is less than 1, forget about the fact that it's x minus 2, but just kind of blur your eyes a little bit. If the absolute value of some number is less than 1, then what is that number trapped between? Not necessarily 0 and 1, but negative 1 and 1. That's right. If I tell you absolute value of some number is less than 1, then for sure the number I'm thinking of in here is trapped between minus 1 and 1. And so that's the next step here, is we're going to pull that guy outside of the absolute value and trap it between minus 1 and 1. The red less than 1 is the ratio test. The ratio test says if your limit is less than 1, then the series converges. Right. So we're making this limit less than 1, or we're figuring out what values of x make the limit less than 1. So every time we do this ratio test on a power series, you're going to put this red less than 1. It's just part of making the ratio test work. Is that like an algebra? Yeah, it's an algebra thing. Okay, and now if you are able to pick values of x that make this thing less than 1, then you will make the original series converge. Now we're going to have some examples that we'll see today where this guy right here was a limit of 1 from before, right? But if that limit turned out to be infinity, then there's no way to pick an x that's going to make the thing less than 1, right? Actually is one number you could pick. In this case, x equals 2 is the only number that we could pick. But as long as we get something not infinity, then yeah, you're right, Ben. We'll find x's that make the series converge. So solving this inequality here for x, what do I do to all 3? Add 2 to all 3 sides. And so we add 2 here, we get 1. Add 2 in the middle, we get x. Add 2 on the right, we get 3. Okay, so what was our vocabulary phrase for this interval? Interval, yeah, domain is good. Interval of convergence, the IOC. If you pick x's between 1 and 3, plug them into the original series, you will get a convergent series. Okay. Interval of what? Convergence, IOC. Okay. Let's talk again about the ratio test. We said if the limit is less than 1, then the series does what? Converges. If the limit is greater than 1, then the series diverges. If the limit is equal to 1, then there's no conclusion. The ratio test was inconclusive if you get something that is equal to 1. And what values of x will make this limit equal to 1? 1 and 3. Those are the two magic numbers, right? So the ratio test doesn't give us any information about x equals 3 or x equals 1. It's not that the series diverges there, it's that the ratio test doesn't apply. So we have more work to do. Really common for the ratio test on a power series is that the ratio test won't tell you anything at the endpoints. And so at the endpoints, we just have to do completely separate tests, old tests from the last couple of weeks. So let's give it a shot. So the ratio test just told you information about the infinitely many numbers between 1 and 3. It gave us a lot of good stuff. It also gave you information about all the numbers bigger than 3 and less than -1. The series diverges there. So the ratio test took care of all of the real numbers, right? You good? All right. Okay, so we're going to test the endpoints. Let's see, what do we want to start with here? X equals, let's start with x equals 3. So what we're going to do is go all the way back to the original series, all the way at the top of the page, and just plug x equals 3 in and write out a few terms and see what the series looks like. So if we plug x equals 3 into the first parentheses, what do we get? 1 minus. Plug x equals 3 into the second parentheses. It's 1 squared over 4, which is 1/4, right? So it's 1 minus 1/4 plus x equals 3 in the next parentheses. Is a 1/9. You see it? Okay, so I'm just going to write out the first 4 terms here. So we said 1 minus 1/4 plus 1/9. One more term. Minus 1/16 plus dot, dot, dot. And we just have to go back to basics and say, hey, this is a brand new series that we are considering for the first time in the midst of this problem, and we just have to do some other test on it. Do not do the ratio test. It will be inconclusive. This is the alternating series test, right? We got this. But I'm going to say, you got this. Use alternating series test, dot, dot, dot. What's the conclusion for this series? Converges. X equals 3, the series converges. The alternating series test with lots more details than I've written up there would tell you that that series converged. The other endpoint is x equals 1. So again, we're going all the way back up to the top. And we're going to plug in x equals 1 and analyze that new series. Okay, so if x is 1, what is this? -1. I'm just going to write some stuff up here. -1. If x is 1, then in the parentheses is -1, but it's getting squared, so it becomes +1, but there was a minus sign in the front. So -1 and then 1/4, right? So very carefully plug x equals 1 into the third parentheses. In the parentheses, what do we get? -1, it's cubed, still -1, and then divided by 9 with a plus sign in the front, so -1/9. So I'm pretty content that we found the pattern here. All of these guys are negative. Yeah? Okay, so -1 minus 1/4 minus 1/9 minus 1/16 minus dot, dot, dot. Again, brand new series. It's the third one we've considered on this page. What test or what kind of series is that? Yeah, that's a p-series, isn't it? I mean, if they're positive. Yeah? Yeah, okay, so then I think if we just write this as -1 times a p-series, what is it, n squared. I won't even bother writing the limits here, but it's the negative of a p-series. In this case, p is 2. What's the magic comparison number? Yeah, it's greater than 1 in this case. So what can you say about that series? Converges. Okay, so putting all of this together, the actual interval of convergence is, so what did we say? It was 1 to 3. And now it's less than or equal to on both of them because both of the endpoints gave us convergent series. Or if you are a fan of interval notation, you guys remember how this works? 1, 3, and then brackets to include, if we weren't including a number, parentheses. Right? Technically, a p-series doesn't have, it's all pluses in a p-series. That's just the definition of a p-series. So we just pull it out. It doesn't change anything. Questions on the process? Yeah. I'm content to just say, so really I should have said is, say like -1 times a p-series, and then we're not using any other test. We're not doing the absolute convergence test. It's just, other questions? So honestly, it looks like a big process, but it's always the same process, and it's pretty routine once you've got a couple of practice problems under your belt. So just a couple of conclusions, and then you will practice. So first of all, going back to this geometric series one, our interval of convergence here was -5 to 5. What number is right in the middle of that interval? 0. On the one that we just did here, 1 to 3, what number is right in the middle? 2. Do you see the 2 in the original problem? In fact, do you see the 2 everywhere in the original problem, right? And so that 2 in the original problem should have, we could now predict, hey, whatever that number is, it was an x -2 in this problem, but we could predict, looking at the original form, we know what the middle is going to be. It's x minus whatever that number is after the minus, that's the number in the middle. And for this guy right here, well, hey, I didn't see any x minuses, so what was the number if we didn't have to write it? Yeah, right, like, I mean, this could have been x -0 to the 4 over 625, right? So you could write all of them as x minus some magic number. What if it was a plus? Something like x plus 7 to the n. What's the center is -7. Yeah, -7. Okay, so move ahead 2 pages from here. In both these cases, the interval of convergence is centered at a. A was just that number after the subtraction symbol. This always happens, and we call the distance from A to an endpoint of the interval of convergence the radius of convergence. It'll be clear with 2 examples here. Remember, the interval of convergence here was -5 to 5. How far from the center to one of the ends? Is 5. The radius of convergence there is 5. In this one, the interval was 1 to 3. How far from the center to one of the ends is 1. And the word radius is kind of might seem like a funny word to use because radius is a circle word, but let's see, 1 to 3 with a 2 in the middle. Radius really means how far you have to go from the center to the edge, right? In a circle. Okay, well, it's, how far do you have to go from the center to the edge? You got to go 1. So maybe radius isn't such a bad word. Okay. So, 3 possibilities for a power series centered at a magic number x equals a. So it is possible the series converges only when x is equal to a, only at the center. Going back, I made up this example a moment ago. Some crazy stuff in the front, some crazy stuff down beneath. For sure, this series converges at what value of x? -7, because if you plug -7 in, what do you get? Everywhere, a 0. Maybe the first term is not 0, but like every term after that is going to be 0, so definitely that's finite. So every single one of our power series converges at the center, -7 in this case. But it's possible for some very badly behaved series that that's the only place where they converge. And if you try plugging in x equals -7.001, all of a sudden it blows up to infinity. And so in that case, part A, the series converges only when x equals a. What would you call the radius of convergence? 0, right? How far can you go from the center to the edge? You can't move at all. And the interval of convergence isn't really an interval at all. It's actually just a single number. I don't know why I can't draw right braces. It's never been able to. Left one, I'm quite proud of, but the right ones, it's just awful. Yeah. Okay, part B, the series converges for all real numbers. It is possible you have a very, very well-behaved series that converges for any value of x that you plug in, anything at all. In this case, what would you say is the radius of convergence? Infinity. And the interval of convergence? Yeah, so -infinity to infinity, all real numbers. If you want to draw a fancy R, you can do that. Chris? Well, with parentheses, it's an open interval. Yeah, if we have brackets around it, it would be a closed interval. Okay, and then finally, if R is finite and greater than 0, the R is just whatever it is. So, but we actually can write something intelligent here. The interval of convergence is, leave a little blank space here. How do you decide what the interval is? Well, your center is A, and then you're going to go R in either direction. So how do I symbolize that? A minus R up to A plus R, right? And then what about the endpoints? Could be either or. So we'll put both. Don't copy this. Don't like share that with anyone. That's not like standard. Like this. That's my way of saying we don't know. It's one of them. We don't know the endpoint. Yeah. So you always need to check the endpoints separately. With some other test. Like today we saw the P series and the alternating series test. Okay. All right. So activity starts on the next page. I will walk around, but raise a flag if I can help. Oh, one quick typo in the answer key. Let's grab this before we start. So find the answer key. And in part A, the starting value here should have been 1, n equals 1 instead of n equals 0.